Modeling data using logarithmic functions. So if the data we have, and this one is interesting thing about tuition fees and that, we're not going to do that, but it just shows, here's a pile of data, and we sketched it, and we see this scatter plot and say, hey, that's kind of logarithmic, that curve, right? It's not exponential, right? It's not exponential growth. It's not exponential decay, right? It's got the characteristic of going from Q4. Now, I mean, Q4 isn't really true because you don't have anything below year 0 in that, but, it is a logarithmic type of graph. So I'm going to give you a different set of data, and we will do this. So not this one, but so here's the set of data we're going to work with. And it's nice. There's 11 numbers. So logarithmic regression. Now on the diploma that they will tell you to run a logarithmic regression or a quadratic or whatever, or exponential, they'll tell you what type. So the data provided shows the average growth rate of 12 weeping Higgins. So I did not make this data up. It's actually for real stuff. Cherry trees. Planted in, so where are there lots of cherry trees? Besides Tokyo. So planted in Washington, D.C. So Washington, D.C. has a lot of cherry trees. So if you're down there at the right time of year, you can see the cherry blossoms, right? Because the trees blossom. It's all very pretty. At the time of planting, the trees were all 1 year old. Trees were all 1 year old. And 6 feet in height. Okay, and then the table we're going to get is going to be sort of the average height of these things, right? And what we want to do is see, is there some kind of a model for this data? And so that's what, so scientists are going to do a lot of is collect data and see if they can model the data, right? Mathematicians collect data or create data, look for patterns in the data, right? And so we're looking for what's happening with these trees and their growth rate and see if we can model that. Okay, so we have two things. We've got the age of trees in years, and we've got the height in feet. So they were 1 year old and 6 feet, 2 years, 9.5 feet. Tree. 1, 2, tree. 5 years, 16.5. So what do we know about trees? I mean, trees like puppies or kids grow a lot in the beginning, and then their growth slows down, right? So there's a lot of trees in the neighborhood here, and you've been going here for 3 years, and it's not like you look out the window and go, wow, like that tree has doubled in height in the last 3 years, right? There's fairly mature trees. It's like, yeah, maybe they're growing, but they're certainly not growing at the same rate they would have grown when they were little trees, right? Things slow down. And that's why we're looking for this logarithmic. We know the shape of a log curve.
the highest x value?
What's the highest which?
X value.
Highest x value is 11. Okay, so we got 11 x values and 11 y values. We're going to put the x values for time into L1, and we're going to put the y values or height into. So I'm just going to enter a few, and then I'll move this out of the way. So we're going to go second mem number 4, which is clear all lists. Stat, edit. So in L1, we want the numbers 1 through 11. In a sec. Just got to enter like the first few, then I can slide it over.
Okay, okay.
Okay. So you'll see, you know, I mean, in the first year, from year 1 to year 2, that, well, you know, it's got to start as a like a seed or something, right? So in 1 year, it was 6 feet tall. Then it gained 3.5 feet, and then another 3.5 feet, then 2 feet, 1.5, 1, 1, a half, half, 0.2, 0.1. So we can see the rate of growth is slowing as the tree ages. We can just plot that data, right? So let's say I just want to go in and we'll set the window. So there's no point in having a negative. This is years, so we've got 0. Let's go out to maybe 15 by 1 is fine. And then minimum height, I don't mind having 0 for minimum. I mean, you don't want anything less than 0 necessarily. And then actually, I don't know, let's go like maybe 25. Say go by 5s. Okay, so I'm going to set my window, and then what I want to do is see the stat plot, right? The scatter plot, just the individual data points. So to do that, I'm going second y equals, and I'm just going to turn this plot on. And everything else defaults to what I want. Okay, and there's the graph. So looking at that, we say of all the graphs that we've looked at, right? Well, it could be quadratic, right? I mean, it could be a quadratic opening down, so that might be something we model. Definitely not linear, okay, or a very poor approximation of linear if it were linear. Okay, it could be cubic, right? Anything that's quadratic could be cubic because it all depends what you're looking at, right? But we're going to be told that it's logarithmic, okay? So we want to run a log regression. Okay, is everybody ready?
Yeah.
Okay, so you go to stat and over to calc, and it's ln reg. Okay, so you won't see log reg. You'll see ln. It's going to do a natural log. So you can just hit number 9, and it says I'm going to run an ln reg. The x list is L1. Yep. Y list is L2. Yep. Frequency list, there isn't one. Okay, so we don't want one. Store regression equation. So you can go alpha F4 enter or vars y vars enter enter. If you have the 83, just do ln reg. It'll have an open parenthesis. Just go vars y vars enter enter. Put in a y1. Okay. So if you got an 83, you're looking at ln reg bracket y1 bracket. If you have an 84, you're looking at this. Go down here, hit calculate. And it runs it. Now it gives it to you in the form A plus B ln x. Okay? And that's how we want to write it. So if I'm going to write this equation out, I'm going to say the equation is y is equal to 6.099 plus 6.108 ln x. Okay, just like that. So all we're doing is taking the numbers, rounding to like the nearest 1,000. Okay, so I've got 3 decimal places. y is 6.099 plus 6.018 ln of the ln of x. And now we can go look, just go back, we could redo the graph. So if I hit graph, this time it's going to draw the line of fit, right? The logarithmic regression. And you can see pretty decent, right? It's a little above in some places, it's a little below. Like if it goes right through the middle of the box, obviously that's the best. This line, it's a little bit above here, and then it's a little bit below here, and then as we go out to here, it's saying it's growing at a faster rate. Like we can see it really slowed down, right? Half a foot, 0.2 feet, 0.1. Like they've reached their mature height where they might not really get that much higher. And we have to realize there are limitations to any model we use, right? This still shows increasing. Okay. So, I mean, what we would do with that is, well, so the usual stuff we do, which is interpolation and extrapolation. So if we want to extrapolate, what will the height of the trees be at 20 years of age? So extrapolation, going beyond the data. What is the height of the trees? When they are 20 years old. Okay, so what do we do here if I want to get height when they're 20 years old? Yeah, I got to put in x is 20, right? Now if I do that, the calculator's going to have a fit because. Yeah, so if I just go second calc value, excuse me, and say 20, you know, this is a fancy way. You think it would know just to expand its window on its own? It's not that smart. So we got to go to window and we've got to expand that. So let's just say we go up to 25 and hit graph again. It's, you know, it can be off the window this way. It's fine with that. It's just if it's off the x value, it's not so good with that. But. Okay, so we go second calc value, 20 years old. And the model, remember, that's what all this is just a model. The model says it's going to be 24.4 feet tall. Okay, so 24.4 feet. Okay, now, do you believe that? They say, well, not like it said 240 feet. I mean, that's what we could do is we could find some other cherry trees around Washington that were 20 years old and just sort of say, you know, are they getting up into that height range, or are they all, you know, maybe there's no trees higher than 20 feet tall. And maybe that's just it, right? It's as high as they go. It's 20 feet. It won't grow any higher than that. In which case we would adjust the model, right? Maybe by setting a parameter on there, setting and just saying the range doesn't go any higher than 20, right? Like we're limited to a height of 20 feet. Another question we can ask is, of course, interpolation, right? Working in between and say when. So interpolation. What's the average height of the trees? At 1.5 years of age. Okay, what do we do to find out height of the trees at 1.5 years? So is 1.5 years, is that an x value or y value? X. Okay, so x's are age, time, right, and y's are height. So we just go second calc value 1.5 and hit enter, and we get 8.6 feet. So there'll be 8.6 feet at 1.5 years of age. And that seems pretty accurate. Right? Like I'm sure if we went back in 1.5 years and measured them, they would be 8.6 feet. So 8.6 feet. Of course, what's the other thing you can ask? You can say, how old is a tree when it's 14 feet tall? So how old is a tree? How old is a 14-foot tall tree? 14-foot tall tree. Okay, what do we do to figure out how old a tree is? So we have to go to y equals and do what?
Set it to 14.
Yeah, set to 14, right? I want to know what's the x value. Oh, come on. I want to know what's the x value when y is 14. So we graph that, and yeah, you're right, exactly. We do the intersect, okay? So second calc, intersect. And we got 3.64. Okay, so it's 3.6 years old. 3.6 years old. Now, anytime we're using a model to represent data, we must be aware of limitations of the model, right? Is it expected this is going to keep going in this path? Okay, we did the grizzly bears and the insects or moth population or something like that. And it's just saying, we need more data. Another 5-10 years, once we get another 5-10 years of data, we'll understand what's happening here as far as what the trend of this data is. Is it cubic? Is it quadratic? Is it just going down and heading down? Is it cubic? So it's just heading down for a bit. It's going to head back up again. Is this logarithmic? Is it limited to the first 12 years? Is this model good for 12 years? And then after that, it's like, yeah, okay, they just kind of top out at 20 feet. So if the age gets any more than 12 years, then the height just stays at 20 feet. So any model you're using, the assumption is it continues along on that matter. Okay, it continues along. So if we were doing population of Calgary, we had the growth rate of population in Calgary. Assuming it continues at that exact same rate, then we can make predictions for years to come. That's kind of what the city's doing, right? I mean, they have to look at the growth rate and figure out what do we need in the way of services. And so the assumption is, well, assuming it keeps going the same way. Okay, one last one to look at. Caffeine is found in coffee, tea, and soft drinks. Many people find it makes it difficult for them to sleep. The following data was collected in a study to determine how quickly the human body metabolizes caffeine. Each person started with 200 milligrams of caffeine in her or his bloodstream, and the caffeine levels was measured at various times. Okay, so we know everybody is not the same. They're all going to metabolize. You're going to metabolize any particular chemical or compound at a different rate from everybody else. But on average, we can say, okay, what kind of caffeine level? So here are some measured levels. We're not going to put this in. We'll just they ran one. We'll just go with it. Okay, but here's the data. So we've collected all of this data from these people, caffeine level in the bloodstream. We measure their caffeine level. Here's the time: 1, 1.5, 5, 3, 6.5. Right? Data's kind of jumbled up.
There won't be one like this on Facebook.
Like that many. I try and keep it down to like a dozen.
Only on the diploma.
Yeah, on the diploma, 27. No, they'll keep it. Determine the log regression. So basically, what we would have done is entered that data. I mean, if you're working in the science lab or something doing this, you're going to have a little more sophisticated programming to enter this. You probably won't be doing it on your TI calculator, but the idea is still the same. So they graphed this, and you could say, well, that looks like exponential decay. right? Kind of. But exponential decay can also be modeled as a logarithmic regression. So they ran regressions, and you'll be told do a log regression. They got the equation, 44.392 minus 8.357 ln. See, so a negative leading value on the ln, like a negative log, drops. That goes to Q1 down to Q4. Now we know this won't drop into quadrant 4. It can't go below 0, right? Whereas a log, a logarithmic curve can go below 0, right? But this can't, because you can't have less than 0 caffeine. And then basically just ask some questions, right? How long does it take to metabolize 50% of the caffeine? Okay, so you put in 0.5 times 200. So how long does it take to have 100 milligrams? Okay, so you draw a line 100 milligrams. You say it takes about 5.9 hours. Okay, so it takes the average person. I don't know if this is for real data. I guess you could look it up, but you could look up the rate at which.
That's pretty accurate.
Is it?
That's about a 6 hour half-life.
6 hour half-life. Okay, cool. Difference between 10 and 9 p.m. The question here was like how much caffeine is left after 11 hours, or let's go see it. It's part C. I'm just curious what we were at. C. Paul drank a cup of coffee at 10 a.m. How much caffeine will be in her bloodstream at 9 p.m. in the evening, right? So knowing, you're going to conduct your own experiment by, it's like I went to Starbucks and I had a large caffeine at noon and then I just couldn't sleep at night, right? So that you may be a slower metabolizer of caffeine, or there was just too much caffeine in that particular drink. And some people could drink a cup of coffee before bed and it just doesn't affect them. So it's just saying, so how much caffeine would be left? And just saying between 10 a.m. and 9 p.m. is 11 hours. Solving the equation, working this out, saying how much caffeine is left after 11 hours, about 54 milligrams of caffeine. Right? And then we would have to look and see, says Paul's only able to sleep if her caffeine levels are below 40 milligrams. And again, everybody's going to be different, right? So everybody has a different tolerance to caffeine, different level of metabolizing caffeine, and so on. When they do studies like this, you do it on a large enough number of people, you come up with some averages. As far as dosages for drugs, certain antibiotics, whatever, again, they do a study on a large number of people, measure how much of the compound is left, and then figure out, okay, this is the average dosage we need to have a particular effect. Key ideas. A log function may be a good set of data if they're increasing or decreasing curve where the domain is restricted to the set of positive real numbers. Okay? Because we know that for an exponential, the domain, is all real numbers. Logarithmic, and maybe you can use either. Maybe the exponential is just as good, right? It's a decay function. For caffeine, it would be a decay. So, 6 one, half does the other. Format. Okay, you run ln reg. Okay, so it's number 9, ln reg. You're asked to do logarithmic regression. Don't go looking for the word log. It won't be there. So ln reg, the format constant plus a multiplier times ln x. That's this form. Logarithmic curve of best fit could be used to predict values that are not recorded or plotted. Predictions can be made by reading values on the curve of best fit. And questions of the day.
Yeah, it's not right now.